Okay, good morning, my dear students. Good afternoon to whoever is watching right now this video. And this is just for calculating some forces in transport equilibrium. The exercise said that there's a mass suspended on those chords, the two chords there, without the angle specifically there. So let's get to work specifically about how to understand and to show the vectors or the forces, because those are representations of the forces, we can't see them. So for getting started, what we have to do in the first place is, like, as you can see in green, my Cartesian plane or my system of reference for pointing or locating the center of this Cartesian plane where the forces are going to be applied. So we have to transport the forces to the path in which all of the forces are going to be located. That's in the first place. So the two arrows represent the two tension forces there for the chords applied to that mass of 50 kilograms. So, and the arrows represent the vectors. So tension 1 and tension 2. That's that in the first place. And for continue understanding this exercise, there's a square I have just drawn there, because if I see that there's 45 degrees in the upper part, I can conclude because of math properties, and that there's 45 degrees also in the other position for those vectors respecting to the system of reference I just drew, which is kind of because of the math. Oh, in other words, we're talking about perfect squares. That in the first place. So the direction of the tension 1 is 45 degrees respected to x, because if 45 is one way, there's 45, and the addition of the 45 plus 45 is 90 degrees. So it makes sense. I'm going to draw a Cartesian plane showing specifically the, I am going to isolate the forces. I am not going to draw the mass anymore, but because the mass is suspended, so definitely is attracted by the earth, and as a consequence exerting a force which is called weight. In Spanish, we call it peso. So the weight comes specifically with that arrow in blue, I just put there. And the weight is going to be calculated with the mass times the gravity according to the second law from Mr. Newton. If you remember that, I just replaced the values, the 50 kilograms of the mass there times the 9.8 meters per second square, which is the acceleration of the earth, normally the gravity, the standard acceleration of gravity there. If you do that multiplication, then we know, since the weight is a vector pointing downwards caused by the mass of the 50 kilograms, is 490 newtons. If we do understand that that force, and the exercise says that the block is suspended there, we can conclude that it is at equilibrium. And if it is at equilibrium, that mass pointing downwards, or 490 newtons, it is annihilated or equilibrated, like at equilibrium with other forces pointing to the upper part, right? So it's annihilating each other. Definitely I need to have which forces are going to be those? The tensions. Let's get to see them. So if you do understand this part specifically, I am going to draw now like the two vectors in red. I just did in the first place. Let's get to show this one. I want to draw them a little bit bigger, just with the purpose of understanding it in a better way. This, and let's draw them with another color, so we have them clear. Okay, by seeing in this case like the 45 degrees with these two vectors, the tension 1, the tension 2, and so on, so on, so on. And I can also see that because of the angles of the application of the two tensions, I can conclude specifically that the tension 1 has the same value that the tension 2, because these two angles are the same. So I can do that because, given the fact that these two angles have the same value, I could say, mathematically speaking, that the tension 1, I am going to write this, but the tension 1 equals to the tension 2. So whenever I calculate those, the two values are the same because they both have the same angle. If the angle were different, then definitely we have to do another analysis. Another thing we know about vectors is that we can actually project the vectors to the axis in green, the y and x. If I do so, I'm going to get this value, and I'm going to use a green, not a green, maybe a sky blue color, maybe this purple. for showing the projection of the tension one. So if we see this vector shown in here, like this one there, this is the tension one in Y. It should be on the X there, but I want to move it a little bit to the left because I am going to have another tension like drawn. This is the tension one in Y. Exactly. This is tension one in Y. Very good. This is this one. And the other one in X. It's pretty simple to draw. That is going to be the tension one in X. Very good. So yes, it makes sense. If you recall projection of vectors on the Cartesian plane. So that's it. But also I'm going to use another color for the projection for the tension 2. It also does project in the XY. So let's use like this orange, purple, this one, left there. Yes, there. I put this projection of the tension 2 in there. It gives me another vector, right? And since the tension, yeah, very good. And since the tension 1 and the tension 2 are kind of the same value, I can easily conclude another math property there. This is the tension 2 in Y. I'm going to finish there. And I am also going to project that in X. Very good. Great. You remember how to draw this projection of rectangles, the squares. Exactly. It's just a module, remember that. Okay, so I just drew that, and by drawing that, I can see that there's two tensions pointing upwards. Those are the ones I am going to pay attention. I have to pay lots of attention because those are the tensions specifically that annihilate the tension pointing downwards. As you can see, there is the tension 1 in Y, right? Pointing upwards. So I'm going to add it to the tension 2 in Y. And that is going to be the same value that the weight, which is pointing downwards. I do not have to forget that both are vectors, so always with the arrow in the upper part. And that's why. So the tension 1 in Y plus the tension 2 in Y equals to the weight. They need to have that addition of the two vectors pointing upwards must be the same value to the weight pointing downwards. So I can conclude the body is at equilibrium. Body remains at rest because the addition of the forces have to be 0 if the body is going to remain at rest, right? Being said so, I also know that the tension 1 equals to the tension 2, and because of the degrees of the 45 degrees, if we do this calculation, it's going to be something really interesting. If the tension 1 equals to the tension 2, because of the degrees, then I can conclude that the tension 1 in Y equals to the tension 2 in Y. The tension 1 in Y equals to the tension 2 in Y. If that is correct, then I could calculate just one of the two tensions, and when doing so, I just pass that value to the other one because both are the same. Let's calculate the tension 1 in Y. Well, by knowing that in the first place, if the two forces are the same, that means it's like having, I could replace like, for the first equation, the tension 1 in Y. If I know that the tension 2 is the tension 1, is like saying plus tension 1 in Y equals to the weight. And if you remember, the weight was specifically 490 newtons. I could say like, okay, so tension 1 in Y plus the tension 2 in Y equals to 490 newtons, right? But instead of tension 2, I put tension 1 once again, because it's the same value, just because of that, remember that. So I can easily conclude that 2 times the tension 1 in Y equals to 490 newtons. Oh, so that means that the tension 1 in Y, right, tension 1 in Y equals to 490 newtons divided to 2, right? So that means it's distributed into the two tensions in Y. And if I do so, that means like the tension 1 in y equals to that division. Specifically, if you're using the scientific calculator, you're going to have 245 newtons. If that is tension 1 in y, since both values are the same, I know that the tension 1, the tension 2 in y equals to 245 newtons. So now that I have the two tensions, right, it's going to be pretty simple to calculate the tension 1 in x, and I forgot to put this value in here, like the tension 2 in x. Those are not important at this moment, but actually they do annihilate each other because the body is at equilibrium or at rest. So we could say that now that I know the two forces, tension 1 in y, tension 2 in y, I am going to isolate these two right triangles because I need to do a double calculation. Let's isolate this right triangle coming from this one. I'm just going to isolate it. Bigger is this one, like this one. So I'm just drawing it at scale. And if this is the tension 1, and I do not know the value, but I do know that this value from that side is 245 newtons. And something amazing about the property for triangles is like if this is 45 degrees, I can also conclude that this value in the lower case is 245 newtons. Why is that? Because since 45 degrees is specifically the division of 90, right? Allow me to explain this in a better way. Take a look at this square, right? Square has 360 degrees. If the diagonal is like this one there, and it is perfect well drawn, then this is 45 degrees. That means this is also 45 degrees. And this happens only in perfect squares, right? So if that is okay, 45 plus 45 is 90. If that is correct, that means this is also 45 degrees, and this is also 45 degrees. Oh, so that makes lots of sense in terms of this one, this one. Okay. For that to be correct, like I said, this applies only in perfect squares. That means this side, if this, like I said, if this side is 245, by definition, this other side must measure or have the same measurement, like the measurement, both are the same. Because this happens like 45 degrees and 45 just in perfect squares. And perfect squares do have the same length of all of the sides. Being said so, that's why I concluded that the tension 1 in y and the tension 1 in x is 245 and 245. If we do follow that idea, then we're ready for calculating the tension 1, because the tension 1 is going to be specifically, so the tension 1, by applying the Pythagorean theorem, you do the square root there. Let's put this there. Square root of what? Of the sides, because this is a right triangle. If you remember, this is a right triangle. In right triangles, for finding the hypotenuse, which in this case is the tension, you just apply the two legs, and that would make it, which is 245, which is one side, to the second power, plus, again, the other side, which is 245 to the second power. So the tension 1 by value basically is going to be, if you insert those values into the calculus, go right up to 105 to the second power, square root 245 plus 245 to the second power, is going to be 346.48 newtons, right? Well, this is for one of the right triangle, the one I just showed you, but there is another right triangle in the right side, and for that one I have to draw another triangle in here, which is this one specifically. This is this triangle there, and guess what? That triangle, the tension 2, has the same properties, right? Has the same properties. Actually, it's exactly the same like the other triangle, because it has 45 degrees, And because we concluded at the beginning that the tension 1 is the tension 2. So if the tension 1 is equals to the tension 2, then the tension 1 in Y is equals, now we said that it's 245 newtons, and if that is correct, then the tension, sorry, it's not tension 1, it was tension 2 in Y. The tension 2 in Y equals 245 newtons. That means the tension 2 in X is also 245 newtons, because that's the only possibility, like I explained in the square, for having the two values have to be the same. If that is correct, we apply the same square root, but for tension 2. And basically, like, actually, you're going to see that there's no need to do that. We already know that both of them are the tensions. I just wanted to repeat this to understand this in a better way. So by definition, the tension 2 equals to 346.48 newtons. That is how we calculated this. And we have found the values of the two tensions, find the values of the two tension chords, and so on, so on, so on. I think you got the idea. Remember to always draw a Cartesian plane, draw the forces acting there. If it is at equilibrium, then all of the forces must annihilate each other or causing a value of 0. And you use the Cartesian plane for drawing the forces acting there, decompose the forces in X and Y, and at the end, you isolate the triangles for applying the Pythagorean theorem, sinus, cosinus, tangent, whatever you want there, which is going to be useful for you. Being said, so guys, I'd like to say thanks for your attention to this video, and that would make it. Thank you. Goodbye.